All right, good morning. So here we are yet again for another lovely session of CENG 4412, Steel and Concrete Design. Today we're going to be looking at our first video, our first look at tension members, or the design of tension members. We have a few learning objectives for today. First, I wish to calculate the capacity of a tension member in the yielding limit state. I wish to demonstrate how to calculate the capacity of a tension member in the fracture limit state. Discuss the importance of the shear lag reduction factor, calculate the capacity of a connecting elements in yielding, and calculate the capacity of connection elements in fracture. And we will discuss the difference between these between these limit states, and define tension members, connecting members, or connecting elements, etc. Okay, so first we need to go through some definitions and look at what we define as both tension members and connecting elements. And connecting elements. Tension members and connecting elements. All right, so well, this shouldn't be any surprise. I think the tension members and connecting elements, the definitions are kind of self-explanatory, but we could be a little more specific. I'm going to abbreviate here tension member as simply TM. And a TM, or a tension member, is simply an element in pure tension. An element designed to carry tension. Fairly straightforward. Now, if you think about it, though, it is literally impossible to have a pure tension element. That is simply not possible in the real universe, if for no other reason than every member has some self-weight, unless there's basically well, I suppose you could have a member under high tension and then have it hanging vertically or something, but in almost all cases, you're not going to have a pure tension element. But anyway, for our purposes here, we're assuming elements in pure tension. And we will later look at how to combine loads together later in the semester, but now we're looking at elements in pure tension and also centric axially loaded members. So in other words, we are assuming that the centroid of the tension load is passing through the centroid of the cross section, so we don't have to worry about any. If your load is not lined up with the centroid of your tension member, then you're inducing some sort of bending. We call that eccentricity. So, in other words, imagine if you have let's say a wide flange shape that you're using as a tension member for some reason. Your centroid of this member is right about here. Now, imagine if I was going to apply for our tension member examples, I'm assuming that the load is also applied right through the centroid. However, if I were to apply the load, say, over here, that would be off-center. I would have a force separated by a distance, therefore I would have some small amount of moment, and that would induce bending in the member, and we don't want to worry about that yet. So again, for our first work here, we're going to just look at pure tension members, keep it simple. Pure tension members, these members are under just a single axial force. All that force is going directly to the centroid of the member. Okay? Next, we can look at a definition for connecting element. And I'm going to abbreviate this, CE. And a connecting element is, fairly straightforward. It is a member, or not a member, but it's an element that serves as a connection point between other elements, between other members. That serves as a connecting element between members, or a connection point. I don't want to use the same circular definition. Connection point between other members, between load-carrying members. Is that perhaps a better way to say it? And I'll give you a few examples, and I will give a few examples of this. Between load-carrying members. So we could have connecting elements that connect beams and columns, that connect compression members with tension members, whatever we have. But in this case here, we're looking purely at those today at least we're looking purely at those connecting elements that connect different tension members. So let me give two examples of this. Examples of connecting elements, or examples of connecting elements and tension members. Two examples I wish to describe are gusset plates and splice plates. So you might have a gusset plate. So a gusset plate is simply a plate, a piece of steel, a flat piece of steel that is used to connect various tension members or other members. It's very common to see these, especially in places like trusses. If you ever see something like this, a plate where several tension members come together, that is where an example of a gusset plate. So again, this is a gusset plate. And then we would have various various tension members connecting to this. So let me show you this here. Maybe I'm gonna draw this as a couple angles going into here. So this is an angle. We have the web of the angle and the flange of the angle here. And then maybe we have another one here. Maybe another angle here with another flange, and then the web of the angle here, and then maybe you have another angle here. Something like this. Very generic. And maybe it's connected. We could connect these via either bolts or welds, but let's say we have bolts, 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 bolts. And then we would have, let's label this again. I'll label this as a tension member, tension member, tension member, and connecting element. If I can manage to write, and connecting element. Okay. Now let me show the loads on here. First, let me show the lines of the centroids of both the, in this particular case, I've lined up the axes of all of these things so that the centroids of the angles and the centroids of the bolt lines all line up along the same line, and that is done to prevent any kind of eccentricity and bending effects. And then I would have maybe some tension loads here, a P, a P, a P, a P. Okay, and so why am I drawing this? Why is this important? And also this is going to be a connecting element here, so I'll go ahead and label that. Oh, that's already labeled. Okay, so why am I drawing this out? What's the point of this? Well, the point of this, at least in my mind, is to illustrate the various ways this can fail. So if we're trying to design a system that has tension members in it, this stuff gets very complicated very quickly. See, these angle irons are not connected directly to each other. They are they're not even connected directly to the gusset plate. The way load is being transferred is that load is being carried via this angle, then it's going into the bolts, then it's going into the gusset plate, and then if load wants to get from this angle to this angle, it has to go from the angle to the bolts, to the gusset plate, to the bolts, to the other angle. So when we design these things, we have to consider many different possibilities. So how many different ways can something like this fail? How can this fail? Well, one, the angle can fail, an angle can fail. And there's more than one way the angle can fail. It can fail in either tension either in yielding, or it can fail in rupture, and we'll learn about that in a bit. But more specifically, or more generally right now, an angle can fail. So what I mean by the angle failing is that the steel in the angle itself could be broken. It could yield, it could fracture, the angle itself could break. Two, a bolt could fail. One or more bolts could fail. Bolts do not have infinite strength. They are, if I give you a structural bolt and ask you to tear it apart with your bare hands, you're going to have a hard time doing that. But with the types of loads we deal with as structural engineers, it's not very difficult to cause a structural bolt to fail if you overload it. So a bolt could fail, or bolt could a bolt could fail. Or three, what would be the third one, do you think? Huh? The centroid, the gusset plate. Yes, the gusset plate itself could fail. The gusset plate could fail. So when we're designing structural connections or steel structures, we need to start looking at this from a systems-wide approach. We don't just have one beam. We don't just have one column. We have things and elements connected together. And whenever you have things connected together, you have to start looking at what is the weakest link, essentially. This connection, of course, it's the old chain analogy. A chain is only as strong as its weakest link. A connection is only as strong as its weakest element. And so when we start looking at connections, I know that's kind of tricky to start off right off the bat to look at connections, but I like that this really is an illustration of how we can start thinking about things in terms of components, in terms of pieces that can fail individually. So at this level of engineering, at this level of your education, you have to start thinking about, okay, what is this actually made of? What is this? This is a real physical thing. In, say, mechanics of materials or even up to structural analysis, we're dealing with very vague, kind of wireframes and wire diagrams and very general things. A beam is just a line or a cross-section or something, but it's not connected to anything except just there's a pin support, or there's a fixed support, that kind of thing. This is where stuff really starts getting tangible. And so we really need to start thinking about how we put things together, how they're formed, how they're made, how they're connected. And so I really think in this class, 4412, Steel and Concrete Design, is where your understanding of structural engineering really starts getting tangible and concrete. Ugh, sorry. Okay, another example. The splice plate. Second example. Splice plate. Now I'm going to draw this thing longer than it would actually be to give myself a little more room to talk about it. But let's say I have two wide flange shapes. And one wide flange coming in here. And another wide flange coming in here. And I need to connect these somehow. And let's say I'm making a pin connection, so I only need to connect the connect the web up. So I'm just going to put a big plate from here to here, and then connect it via bolts. Or I could also connect it with welds, either or. So bolts, bolts, bolt, and bolts. Bolt, 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 bolt. And then I would have a P and a P. And a P. Now, you might think I don't know if this raises any red flags, or not red flags is the wrong word. Causes any curiosity with you, but something that might come to mind is that when we're designing a member for tension, when I calculate how much tension this wide flange can support, I'm going to be looking at the total cross-sectional area. However, though, looking at this plate here, you might ask yourself, why don't we bother connecting up the flanges? I mean, see, look at this. We're only connecting the web. So if we're going to take into account the cross-sectional area of the flange as well, doesn't that mean that the splice plate would automatically have a much lower strength than the wide flanges here? Not necessarily, because there's nothing saying that I have to use a splice plate with the same thickness as the web of the tension member. I could use a greater thickness here, but just depending. But we will go into more detail about how this works. So anyway, again, this would be a splice plate, very similar idea. And I would also ideally, if I wanted to avoid any eccentricities, I would want to make sure that the centroids of my bolt group, so the centroids of my bolt group, the centroid of the load, and the centroid of the wide flanges all lined up exactly or as close as possible. So these bolts will have a centroid. You can have a centroid for anything, even holes. And so ideally, I would make it so the centroid of my bolts, the centroid of my loads, and the centroid of my wide flange shapes all line up along the same axis. If I do that, I avoid any kind of eccentric loading and any kind of induced bending because of that. But sometimes that's unavoidable, but we won't worry about that right now. But there are cases where you simply have to design eccentric connections because of limitations in geometry. You can't always do the ideal case. And this is a splice plate. And we would have wide flange and wide flange, or this could be as drawn. I told you this was a wide flange, but it wouldn't necessarily have to be so. It could be a C channel, or, well, I guess as drawn it has to be a wide flange or a C channel, but anyway. Okay, so if I were to label these again, this would be a connecting element, this would be a tension member, and a tension member. Okay. So next I'd like to draw a free body diagram of how a tension member and connecting element work together, and how we're going to distribute load around and through our tension member connecting element systems. Okay, so let's say, let's label this free body diagram of tension member and connecting element. Free body diagram, tension member, and connecting element. That's so much fun, according to certain definitions of fun. So let's say I have a angle, or an L shape if you prefer. Again, if you're not familiar, an angle, if I look at it from the side, it has a cross section that looks kind of like this. And later on, we will go through some exact, I'll give you some handy tips on, I don't think today, but later I will give you some handy tips on how to navigate your way around the steel manual. And I'll make that in reference to the recent edition, the 15th. Okay, so let's say I have an angle here, and I want to connect this to a column, or really any kind of support, maybe anything that I can treat as a fixed support. I have a load P here. Now, the problem with sometimes connecting, now I could just connect this angle directly to a column. I could just, weld it right to the side of a column, but sometimes that can be problematic, especially if the column doesn't have a flange of the right thickness. So sometimes what you use instead is you use a connecting element. So maybe my column, I'm going to consider my column to be much beefier than this angle here, so enough that I can consider it as a fixed support. So here's my fixed support, but really what this would be in real life would be something like a big, beefy column. But I want to take this, I want to take the tension load from this tension member and deliver it to this big, beefy column. However, again, often I don't want to, I could just have this thing just right up against this thing, butted right up against it. I could just weld it directly to the column. But that would be a very concentrated point load in the column. The column itself may not actually be able to carry that load because it may be a very beefy column, but it might not have the flange thickness necessary to carry that large point load. So instead, I might use a connecting element. So maybe I have a connecting plate. My connecting plate might look something kind of like this. Let me more like something kind of like that. Just a plate. That will give me some more room, some more surface area in order to form a weld or a bolted connection that allow me to join this to the column here. Now this is definitely not to scale. This is a little bit off, but I'm just trying to give myself enough room to really illustrate what I want to show. Okay, so this is what it looks like in general. This isn't really the free body diagram yet, but let's keep it simple and say this is connected by a couple bolt holes. A couple bolted, so let's say this is a bolted connection. And I'm also going to assume that this is a centric loading. So I'm assuming that the point load here lines up with the centroid of both the, I'm assuming the centroid of the angle, the bolt connection, the centroid of the bolt holes, and the centroid of the load all line up with each other. Okay, and this is going to be our connecting element, of course. So I'm going to list my assumptions. I'm going to assume a few things. Assume. First, I'm going to assume that all the centroids are lined up. 1, all centroids are lined up. So again, the centroid of the angle is in line with the centroid of the load, is in line with the centroid of the bolts. And that would not necessarily have to be the case. For example, if I just put 2 bolts here and no bolts here, well, obviously that's not going to be a centric loading. And then And there's another assumption that is reasonable, that becomes reasonable, that becomes reasonable because of the centric loading that I'm assuming. Because of this, I can assume then that all bolts carry equal load. All bolts share the load equally. Share load equally. All bolts share load equally. For tension members, symmetric about centroid. Symmetric about centroid. Okay, so now I'm going to draw a free body diagram of the, you know what, I'll go whole hog. I'll actually draw the big old free body diagram for the bolts, or for the connecting element, for the bolts, and for the tension member. On my notes here, I only have the two, but I only have the elements, or the element and the member. But I'm going to feel fancy and actually draw a third one, including the bolts. So I'll have this. I'll have the bolts themselves. And I'll have the tension member. So this is the tension member. Oh, and I have the bolt holes here. The bolts and the connecting element. Okay, so let's look at the loads here. Well, I have a load of P to the left here, and a load of P to the right. Then here, I'm going to have 4 loads, each P over 4. I'm assuming that each bolt carries a load of 1/4 of the overall load. P over 4, P over 4. Then each bolt will have a load pair of P over 4. P over 4. Then here, each hole will be pulling to the left on the tension member with a load of P over 4. P over 4, P over 4, etc. All these are P over 4. So the bolts experience a leftward and a rightward force of P over 4. So they are actually going to be in shear. Bolts are loaded in shear. The the connecting element, it's going to be in tension, and the tension member is, of course, also in tension. So this is where we can really start to see all the different ways this kind of connection can fail. I can have the tension member fail, I can have the bolts fail, or I can have the connecting element fail. Or, you know, if you really want to be thorough, we could say the column itself could fail too, but in this problem we're assuming that the column is beefy enough that it's effectively rigid, so we can just call it a fixed connection. Okay, any questions on this so far? Yes?
Why don't you draw the column itself as well in that free body diagram?
I could draw the column itself, but I don't know what the column. This question was, why don't I draw the column itself in the free body diagram? I could, but the problem is that I don't know what the column is connected to, if it has other loadings on it. So I'm trying to elaborate on just the connecting element tension member system. Other questions, but good question. Other questions? Okay. So again, we can look at, we'll have to look at the failure modes for each of these. Now we're not going to talk about bolts today. We'll get to that later in the semester when we talk specifically about connections. So for example, for your first exam, I'll just have you assume that the bolts don't fail or something like that. Bolt shear design is something we talk about later in the course. Because we're talking about, I want to focus on tension members right now. But first of all, or next, I want to talk about the very specific ways that a tension member can fail. So we say that we have to be concerned about the tension member failing, but there is actually more than one way this member itself could fail. Now, of course, I do have to repeat this. Now, we did talk about this in structural analysis, but I I would like to remind you, of course, that failure does not necessarily mean that something breaks. That does not necessarily mean that a beam falls apart or that a structure collapses, that kind of thing. Failure, especially things like deflection failure, that kind of thing, can mean failure can simply mean you have too much deformation or too much deflection, or maybe you're designing your structure with yielding as the limit state. Sometimes it's not uncommon for us on, say, your normal everyday loads. Like it's not uncommon to see structures designed with the philosophy that, okay, on the, say for the strongest hurricane a building ever will see in Houston, maybe we design that for the ultimate stress, but then maybe for the everyday loads like the 10-year storm or the 1-year storm or something like that, we'll design it for the yielding state. So basically we'll say, in the typical loadings this building will experience every 5 years or so, we don't want it to ever exceed the elastic limit. So all the stresses remain elastic, and we don't get, again, because with plastic yielding, that is permanent deformation. So it's not uncommon for you to say on certain structures that, okay, on all our regular everyday loadings, let's make sure we don't have any permanent deformation on any of our regular everyday loadings. But for the big storm, or the big earthquake, or the big one if you're out in California or something, maybe there it's okay to have some yielding. All we really care is if we just don't want the building to fall over and kill anybody inside it. Maybe that's the limit state for there. But so anyway, the point being, this is a long-winded way of saying that failure does not necessarily mean a beam literally tears into two pieces, although that is what some of the limit states we'll be looking at today. So that's just kind of a proviso. So let's look at tension member limit states. So the guiding equation that we're going to use throughout this course is QU, Q ultimate, is less than or equal to phi Rn. And as a review from lecture 2, QU is your ultimate load. QU is your ultimate factored load. So it already has the load factors baked in. Phi is your load factor, your relevant load factor for whatever you're designing for and whatever limit state you're using. Phi is your load factor, or sorry, not your load factor, sorry, your resistance factor. Your resistance factor for whatever you're looking at. And R sub n, that should make clear that's a subscript. R sub n is your nominal resistance. Okay, so with that in mind, there are a few limit states we need to be aware of, and this is just for tension members. So we'll look at connecting elements later as well, but I'm talking specifically about tension members right now. The first limit state is going to be yielding. In yielding, yielding is something or is a stress that causes excessive elongation. Excessive elongation. And this doesn't really happen in the connection area. So not in connection area. If you remember your material properties of steel, you have after the elastic limit, you have a very, very long yielding zone. And so in the yielding limit, in that limit state, you're going to have yielding, and what that essentially means is excessive deformation. In the yielding limit state, it's not really failing. It's failing, but it's not really usually being ripped in half. It's just undergoing excessive deformation. And in most cases, that's not desirable for structures, because if things start bending too much, well, think about the building you're in right now. We're on the second floor of a reinforced concrete building. And look around you. What do you see? You see drywall. You see hanging ceiling. You see, well, carpet's not going to mind, but drywall is a great example. See, the thing is, a lot of the materials we like to build our buildings out of are fairly brittle. if you have excessive deformation in your structural elements, a lot of the materials that make up the building, like the, think about it, you've probably seen this before. We see that we have a lot of problems with the soils in Houston, the clay soils, expansive clay soils. And because of that, you often get strong or large deformations in your foundations. And that causes things like cracking in drywall and siding and brickwork and things like that. A lot of the materials that we like to make buildings out of, whether it's brick or glass or drywall, these are fairly brittle materials. And if you have excess deformation, even if the building itself is fine, the structure itself is standing, you might have damage to a lot of your non-structural elements. So yielding is often itself a limit state. So this is yielding that occurs before the strain hardening. You're dealing with just excessive deformation. And we don't need to worry about yielding for the design of connecting elements because even when a connecting element is so small longitudinally that even if you're getting yielding there, the total deformation you're getting in inches is small. Yielding is only a significant limit state if you're dealing with long members like tension members. Okay, so again, you just have a initial length like this. If you want to envision this, you have an initial length like this, you apply a load, and it stretches out. So now it's like this. And you are applying some load P. Okay, what's next? Our next limit state that we'll be considering for tension members, and we will actually look at these numerically. I just need to define and describe them first. The next one is fracture. Fracture is more critical than yielding because this is where something actually is breaking into. This is going to combine fracture and yielding. So in order for something to break into, it has to both fracture and yield. You have to first stretch a surface to the point of yielding and then keep applying load till it actually fractures. So we say fracture, but we're actually saying this combines fracture but also with some yielding. And let me draw this out. So if you have some bolted connection here, and this is being pulled on, and let's say we have maybe another member here that's connecting to. Imagine I have two members, one slightly larger than the other, with some bolts connecting them, and I'm pulling on each of them with a load P. P, P. In fracture, this guy's going to leave and just leave this guy behind. So in certain cases, you don't actually need to completely break the member, or sorry, you don't need to actually stretch the member too much. It just simply fractures. So what will happen is you'll end up with something like this. You'll end up with maybe a piece of this member left behind. And realistically, let's say, maybe we'll just say it's breaks somewhere in the middle. And so we have a jagged edge here, and now a jagged piece over here that's just being pulled away. So we're just breaking the member right down the middle. So P, P, and P, and P. So we just break the member in two. Just cleave it clear across the cross section. Again, we're breaking it clear across the cross section. And the final limit state we need to be aware of is sort of a combination of fracture and shear, fracture and yielding. But I really consider it more of a fracture. But this is block shear, sometimes known as block shear rupture. So in fracture, we are saying that the entire cross-section of the tension member is just completely torn in half. In block shear, a section of the tension member is torn up to pieces. So if you have again, this is also going to combine fracture and yielding. Okay, so let's say we have a tension member connected to a let's say it's connected to a W section with a relatively thin web. Or maybe it's made of weaker steel and the tension member is made of stronger steel. Let's say I have my another, let's say this is just a plate here, a long plate. And I have a W section here. W section, W section. And maybe some bolt holes here. And I'm going to pull on this with load P. P and P. Okay. So in this case, what's going to happen is neither of these members is going, neither this W section or this plate member are actually going to be pulled into two pieces, or are not going to be, pulled in half. Like, I'm not going to have a break line here, I'm not going to have a break line here. Instead, this smaller member is actually just going to rip a chunk out of the bigger member. Or the opposite could also occur. So, in other words, what this looks like after this failure is, imagine I have the W section here like this, the W section like this, and what's been ripped out of this would maybe look something kind of like this. Oh, maybe more like, oh, derp. Maybe like, nope, lost that line. Something kind of like this, where I'm showing that the bolts are clearly being ripped out. And then over here, in the tension member, I'm carrying a piece of the W section with me. So I have this basically chunk of the W section that is now being carried away by the plate. And here are the bolts here. So instead of again with fracture, I am actually cutting right across the entire cross section of one of the members. I'm fracturing this member or I'm fracturing this member. In block shear, I am going to rip out a chunk of this one of the members. And the reason now you might think, okay, well, what's the difference? I mean, if you're tearing out a section, is that different than just tearing a member in two? And yes, it is. And the reason for this is that, think of your failure planes. If this thing is going to fail, if this plate here is going to fail, it's going to fail. It's going to cause, in other words, if it's going to tear the entire, if it's going to tear clear across the cross section, the entire cross section here is going to fail in tension. Here, though, if I rip this piece out, what's going to happen is along this surface, it will be ripped out in tension, but along this surface and this surface, it will be a shear failure. And the amount of stresses that materials can undergo in shear is different than the amount of stress that it can withstand in tension. So that's why it becomes its own distinct limit case or its own distinct failure mechanism, in that it is a combination of both fracture and shear. All right, so any questions on these types of yielding before we start looking at the equations therein?
Yeah, the fact that you wrote combines fracture and yielding simply means that it yields before it fractures.
Yes, the question was the fact that I write that it combines fracture and yielding. What that means is that yes, that it simply means that before it fractures, it yields. There will still be some yielding. I mean, it'll still, but any piece of steel before it can fracture, it has to yield. Even something like glass will yield a tiny, tiny bit before it fractures. Very brittle materials just yield a very, very, very tiny amount before they fracture. But yes, now when we look at connecting elements, we're not going to consider yielding limit state simply because they're so stubby that you're not yes, they yield, but the actual measurement of that yielding in inches is so small that it's not, that yielding itself is not going to cause failure of cracks in drywall or something like that.
Quick question.
Mm-hmm.
The difference between the fracture and the block shear, does that mean that the block shear more like a bad choice of material rather than the bad choice of design?
The question is, does the block shear mean that you have a bad choice of material instead of a bad choice in design? Not necessarily. I mean, you can get either any of these. All of these are factors of material and design, or geometry, I might say. They're all factors of material and geometry. So I can get a block shear or a fracture to happen regardless of geometry. I can make either of them fail. I can make either piece fail in any mode I like if I select my dimensions and my material properties just right. I could use, there's nothing saying I have to use the same type of steel for both my W shape or my W section and my plate. Often they're not. Often there is a table that I'll mention later in the steel manual that actually shows what types of steel are used for different types of shapes. So you may not have, your plate may be made of A36. That's not uncommon at all. So you might be joining a wide flange shape made of A992 and connecting it to another A992 shape with a splice plate made of A36. That's entirely common. So you need to start thinking about, so in the equations that we're going to look at, you'll need to say, you can't just say, oh, this thing has more cross-sectional area, it must be fine. Well, that one with more cross-sectional area may be made of a weaker material. Getting all tongue-tied. So anyway, we'll look at this. So the first thing I want to look at is tension member yielding. Let's look in detail at tension member yielding. So again, first what I did was I described each of these, and now I just described or defined each of these, and now we're going to start looking at the actual equations. So we see equations for the first time today. Well, I guess we looked at that in the third video, the wind loads video. There were plenty of equations. Okay. But anyway, so tension member yielding. So again, I'm going to put a big old box here to emphasize that this is a tension failure. Just for emphasis, or emphasis if you prefer. Okay, so the governing equation for this is this here. Phi Pn must be equal to Phi Fy Ag. What is all this? First of all, let me cite where this comes from. This is directly out of the steel manual. And this is D 2-1. And you can find this on page 16.1 -28, if I updated my references correctly. Okay, so as we discussed in the second lecture, the difference between load factors and resistance factors, this phi is always going to be a resistance factor, and it's always going to be less than 1. The load factors are going to be baked into your ultimate load, your say your Q ultimate or something, or your there. So now we can start seeing here how the code chooses different resistance factors. So the resistance factor that you're allowed to use, or that you're going to use, is going to depend on both the type of structural element and the failure mode. So in this case, the phi, your resistance factor, is going to be 0.9. So yielding is a slightly less critical failure mode than fracture is. So with yielding, you're allowed to use a larger resistance factor than you are with fracture, as we'll see later. So your resistance factor here, again, the resistance factor is to account for variability in resistance. So you may design it thinking that if you have a certain resistance, maybe you design it thinking, okay, according to my calculations, this member, if built properly, will be able to resist a tension load of 2,000 pounds. But there is always some variability. Maybe the steel that you get from the mill turns out to have some small defects in it. Maybe when they install it, they don't put exactly the right amount of tension on the bolts. Or maybe when they install it, they cut it a little bit too short, and it ends up having slightly different cross-sectional area than it should. So that is what your resistance factor is meant to account for. It's meant to account for small but inevitable variances in the resistance that's actually present. Questions? Yes?
Isn't that equation independent of the resistance factor, though?
This equation here, yes, it's going to be independent of the resistance factor, although not necessarily, because at least here, phi PN, yes, this part is, but this part isn't, because yielding, we're using the yield stress. With fracture, we're going to be using some ultimate stress as well. Okay? Other questions? Okay, then Fy is going to be your yield stress. Your yield stress. And AG, A sub G, is your gross cross-sectional area. Gross area. Gross meaning the opposite of net. So it is the total cross-sectional area. So if we're looking at yielding, we're saying the entire cross-section of our tension member is going to be yielding. So there's that. Now, if you want to get a list, so where do you find this stuff though? Where do you find your yield stress? Now, you could Google it or something, but, questions? Yes?
The equation you referenced doesn't have phi in it.
Okay, yes, the equation I referenced doesn't have phi in it. That's true, but I'm kind of baking it into it. I'm modifying it slightly. Okay, let's go to 16.1-28 and take a look. So it does say Pn equals Fy. All that it's true. All D2-1 says is P nominal equals FYAG. I have tacked a phi onto there because it does say right below there what phi to use, but I just sometimes feel it can be beneficial to show how the phi works together with this, especially if you're seeing resistance factors for the first time in this course. Does that make sense? Okay. Clear as mud. Okay. So the question then becomes, the question that's raised is, where do you get this Fy? Where do you find the yield stress? Well, have no fear, the steel manual is here. And there's another place in the steel manual that you can find your yield stress. Welcome to the steel manual. So you can find this in a table on, on page, let's see, this is going to be, it is table 2-4, if I got my reference correct, 2-4 on page 2-48. So to find your yield stresses, Fy or F ultimate, Fy or Fu, you go to table 2-4 on page 248. So if you have your steel manual, please open to that. Go to page, let's see, chapter 2, page 48. And this, of course, is in the 15th edition of the manual. And it will be table 2-4. So, applicable ASTM specifications for various structural shapes. So, what this tells you, this is a very nice table. It tells you a few things. So, it tells you for each different type of steel that is made in America, is made by American steel manufacturers and also other steel manufacturers as well. These are not exclusive to the U.S. But this table, so if you don't have a steel manual yet, please gather around somebody who has one if you could. Get up and wander around and mingle, be friendly. Come on, get up. It's a group class. Come on. Okay, we're having a bit of fun here. Okay. Okay, so huddle around, gather around, get a little, all position around and gather in front of a steel manual. I probably could, yeah, but I don't have the stuff with me right now. But, okay. Or, actually, yeah, maybe, well, I'd have to email it to myself, but, okay. Anyway. Okay, guys, let's take a look. Okay, do y'all have one back there? Yeah. Okay, so, again, page 2-48, take a look. Look at what we have here. We have all the various types of steel, including both carbon and high-strength low alloy. Remember how we talked about that on the first day of class? There we go, they're right there. And so, look at, for example, A36, common carbon steel. It's been used since the dawn of time. And notice you have two columns. You have your Fy, that is your yield stress, And you have F ultimate, that is your ultimate stress. Fy, of course, that's your yielding point. That's where it's, that's the end of the elastic region. That's where it's going to start yielding and undergoing permanent deformation. Fu, the ultimate stress, well, it's called Fu for a reason. That's it. That's all you ever get. Past that point, well, Fu. So, anyways, sorry. Sorry. Well, it's actually called that because it's the ultimate stress, but, you know, if you're exceeding that point, you're not having a good day. So, anyway, thought you might appreciate that. But this table also lists for which applications each of these steels is currently used. So, for example, A36 is used for basically everything. So, A36 is used for essentially everything. You'll see it for all over the place for W sections, M sections, S sections, C channels, angles, L area angles, etc. It's just used for everything. Now, the dark dark shading is indicating that that is the preferred material. The lighter gray shading is not necessarily preferred, not necessarily the ideal, but it is still sometimes used. But anyway, this really goes down the line of all the various types of steel that you'll encounter. And so this is one of the, what you'll want to start doing as you, what you want to get is go to go to like Office Max or somewhere, get one of those packets of like those little flags, those little sticky flags that you can put in a book. And you're going to want to start flagging your steel manual because especially when you're working through the exam, you will be allowed to have your steel code and your concrete code, your steel manual and your concrete code. And, well, it's an open book exam, but that's not going to help you a lot if, you don't know where things are. So you definitely want to start flagging your manual. And I actually will provide later a list of some recommended flags that you might want to put on for there. So anyway. As you go through your homework and such, you'll want to start looking at this. Okay. Anyway, that's what I wanted to show you right now, but okay. So the steel manual is going to be, just like the concrete code, this is going to be an exercise in page flipping. We're going to go back and forth through multiple different things. The steel manual has various areas that reference other areas and other pages, so you'll find yourself constantly going back and forth between different things. It's beautiful. Anyway. Okay. It's an accountant's dream. Well, maybe not. Maybe nightmare. Okay. So again, this is going to be your gross area, and then another note that you might want to know. Where do you? Okay. In terms of where you find the member properties or the section properties, you'll want to look in Chapter 1. Chapter 1, this covers basic properties. So Chapter 1 lists all your basic properties. These are your cross-sectional properties. Things like all the dimensions. The nice thing about this is, unlike in mechanics of materials where you had to do a lot of calculation of, say, remember calculating moments of inertia and such in mechanics of materials or structural analysis? Remember how tedious that is? The good thing about this class, at least, well, you will have to do that a little bit. You will have to do that a little bit with concrete, but at least with steel, all of your standard shapes, your moments of inertia, your cross-sectional area, your essentially all of the section properties that you need to calculate or that you need to use, almost all of them, with a few exceptions, are essentially already calculated for you. They're listed in a great big table in Chapter 1, and you can just go through there and say, if I want to know the cross-sectional area or the moment of inertia about either axis for a certain W shape, I just look it up. I don't have to calculate it every time. That would get very tedious. And so what you have here, examples of things in Chapter 1, you'll have a table for W shapes, wide flange shapes. You'll have a table for C shapes, C channels. You'll have a table for angle irons, L shapes, etc. Okay. One other note that I want to give before we move on to the other limit state, a little bit of a side note on the loading here. Notes on the code. Note on AISC code. Note on the AISC code. Okay. For a long time, the early editions of the manual, in case you're not aware, the steel manual has been made for quite a long time. This is the 15th edition, but, you know, the next edition won't come out for 5 to 10 years. I mean, these don't come out very often. So 5 years, 10 years or more.
So this good for less than
This,
5 years?
this, depending. I mean, it's depending. Depending. But usually, I mean, these are not textbooks. They don't put one of these out every year. Anyway, in terms of this, like, yes, this is the 15th edition, but realize they've been making the first edition of the. Do you know when the first edition of the Steel Manual came out?
1920.
The 1920s at least. So the first edition of this, they've been making these steel manuals for nearly 100 years. So yeah, that's something to look forward to. As if you go into the practice of structural engineering, you can look up the exact year, but sometime within the next 10 years, you'll be able to celebrate the 100th anniversary of the steel manual and have a party, and it'll be great. And anyway, it'll be lovely. And we can hold a party and have cake and dancing and much jubilation. But anyway, if I'm teach.
Form of code.
Yep. Anyway, so the point being that they've only had 15 editions of this over the course of almost a century. Okay, so the early editions of the manual were all ASD, allowable stress design, using just a single factor of safety for different types of things. And again, in lecture 2, we went into the difference between ASD and LRFD. Then for several editions, they had separate manuals for both LRFD and ASD. Starting in the 13th edition, 2 editions ago, the Black Steel Manual. So the Black Steel Manual was the 13th edition. The Maroon Steel Manual was the 14th edition, and now I guess, what would you call this? Aqua, bluish, light blue. This light blue edition is the 15th edition. And starting in the 13th, the LRFD and ASD are combined into one code. So there are actually ways to use it. As you go through the manual, say the chapter we're looking at here, you can actually see that there are ways to apply these equations in both LRFD and ASD. So if I look at, let me go to 16.1-28 again. 16.1-28. There are ways to apply this in both LRFD and ASD. So if you look on here, you see there's that, I've listed the phi factors, but there are other factors that have that omega on there. And what that is that is a factor for ASD. Don't worry about that. For this class, all I want you to know is LRFD. It's the more modern versions. So the modern code, the 15th edition has both LRFD and ASD. But for this class, you only need to know LRFD. And so, anyway, of course, the older manuals used only ASD, and you know, I only need 3 more manuals, and my collection is complete. So I have in my office, you can see them. I have every steel manual except for the first 3 editions. But anyway, I'll have to get a hold of those other 3 at some point. If you're ever in the mood for collecting steel manuals, if you ever want to take up that hobby, very weird hobby, but up until the first 3, they're fairly cheap. You can get like older editions for $20-$30 on Amazon usually. After that, the reason I don't have the first 3 is those are kind of expensive, so that I can't just splurge on those. I have to budget for those. I think the first and third are about, last I checked, were like $200 or something that I could find. The second edition, though, is actually the really rare one, the most expensive one. The only time I've ever seen one for sale is like selling on eBay for $500 or something. And that's because it was only published for a few years during the Great Depression. So there weren't a lot of copies of it sold, and there's not a lot of them floating around nowadays. So anyway, or maybe somebody in the Great Depression burned them for fuel or something.
$10.
Huh?
$10.
$10 for what?
First edition.
Really?
1 copy.
You found a first edition for $20 for $20. Ooh.
I don't know if they're trying to scam you, but
I might should buy that. Okay, anyway, sorry. Okay, this class is now officially off the rails, but let's keep going. Okay, so next, I want to work through an example of this. Wait, are we there yet? Yes, I want to work through a quick example of this. Here. Let's look at this. Okay, I want to work through an example of how we would check a member for yielding. And I'm going to use an example that effectively forces yielding failure. And basically by doing, the way that I'm going to do that is by, is that I'm going to look at something that's welded, that has welded connections. And I'm basically going to say my load applied is going to be whatever load is needed for yielding. So let's consider this a simple example. Simple maybe being a relative term. So let's say I have a flat plate A36, flat plate made of A36, connected to two connecting elements, or joined to two connecting elements with welded connections. Welded connections. Welded connections. So I just have a flat plate. Let me draw this one like this. That's really bad. Kind of like this here. And the connecting element, maybe more like that and that. And maybe another here. And kind of like this. And I'm going to weld it just here. So effectively by doing this, I'm basically, because of this very particular type of connection, I'm essentially, I am basically forcing this thing to fail in the yielding state. Because it's only connected at its ends, so it's not really going to undergo fracture. Anyway. Okay. So let's say we have a connecting element. Yeah, no, you can't do this in design, but I'm just basically forcing it to happen. So, anyway, tension member. So I have a tension member and two connecting elements. And let's say there's a certain tensile load T applied. T. And let's say this is 50 feet long. So we have a 50-foot long plate, big old thing. Really long plate, 50 feet long. I don't know why you would build such a thing, but I suppose you could if you were inclined. It keeps bouncing around. Okay, so let us say that the T is equal to T yield. T, the applied tension load, is the yield load. Basically what I'm trying to do is I want to look at how this fails, or in terms of how stress is applied and how the strain works with this, etc. So let's look at this. I'm going to look at this as like sort of a method of sections. If I cut this here, and when I say T yield, I'm talking the yielding of the tension member here. So what's going on here? Well, I'm going to have, if I look at this from a cut, because this is that yielding, I'm going to have an overall force equal to just my T sub yield, whatever that is, but all the way across the cross-section then, I'm going to have sigma y. There's going to be yield stress all the way across the cross-section. Sigma yield. Okay. So let's if in this case, what I really want to, the real point of this is that I want to see what kind of deformation yielding actually looks like. How much deformation does this actually produce, even on a 50-foot long member? So epsilon y is going to be equal to LF minus LO. Again, I'm using, just like we compared in lecture 1, or the second part of lecture 1, the difference between engineering strain and real strain. We're using engineering strain here, over L naught. So this is essentially delta L over 50 feet. Delta L over 50 feet. Now, let's find the yield strain. So again, we know that strain is equal to stress, sigma, over modulus of elasticity. Now, thankfully, while we do have different material properties in terms of yield strength or ultimate strength, we don't have to worry, or ultimate stress and yield stress, are, as we go through steel design and reinforced concrete, the modulus of elasticity of steel remains the same regardless of the grade of steel. Now, yes, there would inevitably be small variations, but it's close enough in almost all cases that we can just consider the modulus of elasticity for all forms of steel to be 29,000 KSI. 29,000 kips per square inch. So, this will then produce that epsilon yield is equal to 36 over 29,000, or 0.00124, dimensionless, or you can think of it as inches per inch. Okay, then we're going to use this over here. And I know, because this is this epsilon y is the same as this epsilon y, so I'm going to say 0.0024, or 0.00124, equals delta L divided by 50 feet, and the overall change in length in a yielding case is 0.7, it's going to be 0.062 feet, or 0.744 inches. So the actual change in length of this thing is going to be less than an inch. Even on a very long member, it's very rare to see a tension member that long, 50 feet. There may be some cases like long span bridges or something, but 50 feet is very long for a member. But even at the yield state, and notice I didn't even care what the actual cross-section of this is. This is the actual change in length is independent of the cross-section. It's, if we just say it's, at least for the case of yielding, it's independent of the cross-section. So this ultimately is when we start looking at connecting members, or sorry, connecting elements, we're not going to need to look at the yielding limit state, because the 0.744, is that excessive deformation? It's sort of in the eye of the beholder. In terms of the code, yes, it is. You're not allowed to go with deformations that high. But even on a 50-foot long member, we only get a deformation of 3/4 of an inch. Now, the code says that's all you're allowed to use, but really, that shows you that this is why, with connecting elements, we really won't need to look at this. Okay. So let's say here that let's compare this to the connecting element or yielding of the connection. Compare this to connecting element in yielding. So this actual connecting element here, I kind of exaggerated the size of this thing. So it's hard to say what the exact length would be, but it wouldn't be unreasonable to say that the connecting element here, okay, because what is the gap between here and here? You're not going to actually have a massive gap, because the whole point of this connecting element is to connect to something else, maybe a column or something. So you're not going to have a massive, massive gap in the connecting element here. I drew this as wider than it would actually be in order to give you just to make it clear and to give myself more room. But the actual gap between here and here, this is not to scale. This might only be like an inch. So that's not unreasonable to say this element length here, from the connecting point to the edge of here, may only be a single inch. So I'm going to say that the original length of the connecting element is only 1 inch, at least the length of the loaded portion of it. So delta length in the connecting element may be just the same yield strain, 0.00124 times L naught, but L naught is 1 inch. L naught is 1 inch, so then my delta L in the connecting element is only 0.00124 inches. Look at that. It's tiny. The actual change in length of the connecting element is almost nothing. So this is why when we design connecting elements, we will only need to worry about fracture. We won't need to worry about yielding, because the actual change in length, because the yield limit state is a displacement or a strain limit state. With connecting elements, it's those elements just don't have the physical size necessary for the strain to be important. Okay, questions on this? Okay. So next, I want to look at the next limit state, which is going to be tension member fracture. Tension member fracture. Well, I guess I'll do this on the next slide. So let's go back and describe what this is again, just a brief review, a reminder. So fracture again is where we are, this is not a displacement limit state or a strain limit state, it is a actual, we are tearing this thing in twain. We are taking this and actually tearing it. And the difference, of course, between fracture and block shear is that block shear is going to tear a chunk out of something, while fracture is going to tear right across the entire cross section. Okay. But this is where things start getting a little complicated, and we'll see that. Okay, so in the nice thing about the yield limit state is that it's the simplest one, and the reason for that is that you can use the gross area. However, the equation for this is going to be here. If you want to look, go to 16.1-28 again. And we get the equation that phi, Pn, is equal to, and I know it doesn't have the phi on there, I'm adding that to this, is equal to phi Fu Ae. Okay, so what is this? Well, first of all, phi, of course, is our resistance factor. Well, let me give a citation for this first. This is going to be, this is equation number D2-2 on page 16.1-28 of the 15th edition of the AISC Steel Manual. Okay. Now, let's look at this. Notice immediately the very first thing that stands out to me is the phi. The phi in this case, the resistance factor, is 0.75. Now you can start to see, the reason I like beginning with tension members is it can be tricky, but it's still relatively simple in terms of some of the, at least compared to say some of the later equations we'll see. And so it's a really good introduction to the basic philosophy of the steel manual. That's why I usually start with it. And so you can see here, if you remember back in yielding, what phi did we use? We use 0.9. Why do you think that is? Why do you think that is? Which do you think is more critical? Which do you think is worse? You have too much deformation or your thing literally breaks in half? Well, yeah, fracture is worse. I mean, yes, it's bad if, you have a lot of deformation and maybe people are bothered by it, it creeps people out or something, or there's, enough deformation that you get big cracks in your brickwork or something like that. That's not good. That's still considered a failure, but at least something's not falling on somebody's head. So that is why we tend to have a higher factor of safety, not factor of safety, need to be more precise with my language, a lower or a more critical resistance factor for fracture. It is a much more dangerous failure mode. Okay, and so now notice though, we're not using the yield stress anymore. We are using the full FU. We are using the ultimate stress. Oh great, what have I done? Now the whole semester everyone is going to be laughing when I say the word FU, F sub U. Oh boy, I've created a monster.
Upload this on the internet too.
Okay, so now what is AE though? So we're not going to use gross area anymore. We have to use something called AE. And if you look in the code, AE is the effective net area. Okay, so that raises the question, what is the effective net area? Well, let's see here. The effective net area, AE, is going to be, and I believe this is laid out in, let's see, it's laid out in another equation, in D3.3-1, and that is that AE equals U times AN. And this is equation D 3-1. This is equation D 3-1 on page 16.1-29. Now, so you quickly see how the steel manual is starting to operate. It's going to have equations that then reference other equations that then reference other equations, and sometimes those equations will reference tables somewhere. So the steel manual is this big, kind of ball of twine that you have to get your head around. So this is why it is really important to start practicing with it, becoming familiar with how all this works together. It's sort of a Rube Goldberg machine of lots of different moving pieces. So, well, not really moving, but lots of pieces. So, then in turn, what is this stuff? What's all this stuff? Okay, so U is a factor that we need to add, and this is the shear lag reduction coefficient. And so we'll have to define that. The shear lag reduction coefficient. And what is AN? That's not area nominal, that would be too easy. Area, yes, exactly. It is the net area excluding holes. So we'll have to look at how to calculate that. So I need to use further equations and tables to find each of these things. So we need to use this is our final equation that we're going to use, but we need this element that's defined by another equation, and so then to get each pieces of this equation, we need to use other equations. Welcome to the steel manual. Isn't this fun? Welcome to steel and concrete design. Okay, so let's tackle effective net area. Okay, so net area, or effective net area. So I'm going to give you a formula, and this is based off of maybe not an explicit equation, but it is sort of an equation that comes out of the text that I will reference. Okay, so let's see. And to see this, you might go to, I believe, B 4.3, 16.1-20. So this is explained on page, in section B, or B 4.3b. So this is explained in section B 4.3b. So again, B 4.3b. It's very legalese. And this is expressed, in language, but I'm going to express this more as an equation. And this is 16.1-20. This is page 16.1-20 in the 15th edition of the manual. Okay. Now you can read through this, and says that you basically, to get the net area, you take the gross area and then apply some subtractions and additions to it. But I'm going to explain what these mean here. Okay, so it explains this not as a unified equation, but kind of as just a series of worded explanations. But I'm going to list this as an equation. Area net is going to be AG, that's the gross area, minus the area of the holes here, and then plus the summation of the bolt stagger factors, which we will talk about next lecture. But it's basically a summation of these factors, S squared divided by 4G, and we'll discuss this next class, times the thickness T. So S squared divided by 4G, these are basically factors that relate to the geometry of the stagger of the holes. But then the equation for the area of the holes, this gets a little bit tricky. So we need an equation for this as well. So area of the holes, to go along nicely with FU. Anyway, this is going to be D sub B plus 1/16 plus 1/16 inches times the thickness times the number of holes in the load path. Number of holes in the failure path. So what does this mean? What's going on here? Well, this is the T here is the actual thickness of whatever plate you're looking at or whatever flange or web that you're bolting to. dB is the actual nominal or diameter of the bolt that you're using. The 1/16 is the nominal hole size. And this other 1/16 is to account for damage, material damage. So here's the thing. What happens if you try to put say you have a 1-inch diameter bolt. What happens if you drill a hole that is exactly 1 inch in diameter and you try to put that bolt in there? It's not going to fit. You need to make sure that your bolt has a hole, your bolt hole is slightly larger than your bolt. Otherwise, it's just not going to fit. So typically how we do it, now there are different ways to design bolt holes, but a good rule of thumb, unless you're not, a good standard rule, unless you are not doing something specific, is to assume that the bolt holes are always going to be 1/16 inch larger than you're going to try to drill a bolt hole 1/16 inch larger than the actual bolt hole, or the actual bolt. But here's the issue though. Drilling especially drilling through steel, I mean, it's a rather violent process. I mean, you're shearing material planes apart, you're shearing things. So essentially here is your actual bolt diameter in the middle. Then you have your bolt hole that you're making, which is 1/16 inch wider than your bolt. But when you go and drill a bolt hole when you drill a hole in a piece of steel, you cause a lot of damage. And so you cause a lot of little minute cracking, little minute fractures. You may not be able to see it with the naked eye, but you're in that immediate area, that tiny little, if you were to look at it under a microscope, you would see, elsewhere in the material, far away from that hole, you might have nice even grain structures, everything is cool, cooled nicely and heat treated nicely, etc. But everything around that bolt hole is just going to be completely mangled at the, crystal level. And so basically we say that around this, not 1/16 all around, but like we just add a 1/16 of an inch around. This is exaggerated. There's basically tons of damage caused by the hole making process. So we're just going to say, you know what? We know material is probably there, but it's so messed up and jumbled up and that we don't want to count it. We don't want to account for that in terms of structural strength. Okay. So this is the formula that we're going to use to actually calculate the area of the holes. And then we'll use this shear lag factor, this bolt stagger factor to calculate the overall net area. And we'll discuss that later in class. Okay. So I next want to talk about, we're not going to finish this completely in this class, but I do want to talk next about the shear lag reduction coefficient. This U here. What does this mean? Shear lag reduction coefficient. The shear lag reduction coefficient. Okay, so first, let me draw a generic set of tension members connected by a connecting element, or joined by a connecting element. So we could ignore right now whether it's joined by bolts or welds. Doesn't really matter for what we're talking about right now. Doesn't really matter for what we're talking about today, or at this moment anyway. So let's say we have a connecting element here. And let's think about how stress actually moves. Stress flows. Stress moves. It bends. It flows around shapes. If it took me for mechanics and materials, you would you saw this. Stress flows. It moves around obstacles. It bunches up in spots where there's no. If it has to go around a hole, it bunches up near the hole. You get stress concentrations at certain locations. So that's why in something like in buildings, it's not uncommon to see stress cracks near windows. When you're like wherever you have a interior right angle in a building, like where you have foundation issues or something, you always get stress cracks right near the interior corners of windows, because those are stress concentrations. Because the stress present in the material, in this case the drywall or the brick, has to flow around that opening, and so stress flows. And so let's think about how stress is going to flow through that connection. And this would be tensile stress here. So let's say over here we have the entire cross section engaged, like this, in tensile stress, and same thing over here, like this. But it all has to get here. There is no material here or here to carry that tensile stress. So instead, the stress has to flow. It has to concentrate and flow through the material, or flow to get concentrated enough to pass through the smaller member. The stress has to concentrate. So the point of this, though, is let's think about this, though. Let's consider fracture. What if I'm analyzing this member here for fracture, the larger member? If I'm analyzing this for fracture, what's the problem with assuming that, okay, I'll just use this cross-sectional area here? Can you see the problem with that?
That area's not being used.
Well, at some location, the entire area is not being used. Look at this. Right before the, stress does not just instantly move. It takes a certain distance in order for the stress to become concentrated. So right at the intersection here, this part and this part of the wide flange shape here is carrying little to no stress. All of the stress, before it can enter the bolt holes and be transferred to this member, the connecting element, the stress first in the W shape itself has to be concentrated so it can flow into here. So the critical cross section for fracture for the wide flange shape really isn't way over here. Way over here, yes, the entire cross section can carry tensile load, but here it has to bunch up, it has to concentrate. So this is stress concentrations. And this really is what the U factor, the shear lag reduction factor, takes into account. Now, thankfully, you don't have to derive this in any way. To actually determine these factors, the formulas for these, well, I mean, you have to calculate there's equations you use, but this is a very complex phenomena. As you can see, the idea of deriving from base principles, the shear lag reduction factors would be quite involved. So how this comes about is through the equations that you'll see come about through years of laboratory studies and things like that. Almost everything in the steel manual, or most of it, has come about through many decades of structural engineering professors, essentially, and also people in industry, researching various types of members, types of connections, etc. But anyway, so the U factor here, how do we get this U factor? Here. Yes, we have another table that we can use to get a variety of factors, a variety of equations for various factors. So the U factor, and this is going to be on, let's see, this is on table D 3.1, and that is page 16.1-30. 16.1-30. So if we go there, 16.1-30, we have a table of how to calculate the U factor. And there are various equations depending on what type of system you're using. Now, for tension members, for all tension members except HSS shapes, and you can read some of the provisos therein. The relevant formula for this type of problem, a tension problem like this, is going to be that U is equal to 1 minus X bar over L, where X bar, let's define each of these, and L, where X bar is the perpendicular distance from centroid to connection, to plane of connection, or to connection plane. It's perpendicular distance from centroid to connection plane, and I will illustrate what this means. I think I have to draw it really to explain it. To connection plane. And L is the length of the connection. So let me illustrate X bar first. So if you have if I'm checking, imagine I'm checking for fracture a angle iron up against another plate here, another element here. And I'm looking at this through the cross section. Maybe there's a bolt hole here. Our connection plane is right where at the surface where the two elements meet. So the connection plane is here. This is the connection plane. Then at some other level, some other location, the member that I'm investigating, for the drawing here, I'm going to say I'm checking the for this analysis, let's say I'm checking the angle here now this isn't an angle here, but just an angle, for example. Let's say I'm checking the angle for the fracture, and I would have the centroid of the angle might be somewhere like this. So that's where the centroid of the angle might be, and then my X bar would be the perpendicular distance from the centroid of the element that I'm looking at, the centroid of the angle, to the connection plane. So that would be my X bar here. It's the perpendicular distance from the centroid of whatever object or whatever member you're analyzing, whatever tension member you're analyzing, to the connection plane. Okay, so that is your X bar. And now I need to define the L, the length of the connection. It's not the length of the member, it's the length of the connection. Okay, so I'm going to draw a really bad isometric projection. Really lovely 3D drawing here. So imagine I have an angle here, and let's say there are a couple bolt holes in this. Here, here, and here. In this case, it would be the center-to-center distance of the bolt holes. So it would be like this here. So this would be the length of the connection, the center-to-center distance of my bolt holes, the innermost bolt hole to the outermost bolt hole. This would be my L in this case. If you had a welded connection, then it would be the length of the longitudinal weld. Okay, questions on that? Okay, so there's that, and I just have one other thing I'll talk about quickly.
So, for example, you gave us a problem.
Mm-hmm.
Do you give us the X bar and an L, or we have?
The question is on a problem, would I give you the X bar and the L? I would probably ask you to figure that out, especially on certain problems where the geometry is very clear. Okay. I would probably ask you to find the X bar and the L, yes. And don't worry, we'll have plenty of examples of this. Okay. So then I just want to give one final note. One final note here. Here we're looking at the net section. I just want to say, so why doesn't yielding control the net section? Notice for yielding we only use the gross section. We're not using, for the net section here, when we're taking into account bolt holes and stuff, we are only looking at fracture, not yielding. So why doesn't yielding yielding control in that section. And this will be my final note for today. First, the main thing is that you have a small length. So that means a very small delta L, as we saw earlier. Small length, and that, of course, means a small delta L. And so because of that, stress-strain, if we look at this from the point of stress-strain, strain rapidly goes into strain hardening. Because of this small length, the strain rapidly goes into strain hardening. Because of the small length, we're going to rapidly enter strain hardening such that fracture can occur. Because of the small L. So that fracture can occur. In other words, you can also think of it as a bit of load redistribution. Can occur. Otherwise, it's an example of load redistribution. Because the connection length is so small, load will rapidly flow around it, and it tends to just immediately go into fracture before it has time to really, or not necessarily time, but distance or displacement to really go into yielding. Okay, so any questions on any of this? Well, that was a lot, but welcome to Steel and Concrete Design. Okay, that'll do it for today, and as always, thank you.